In this video, I'm going to go over the concept of hyperconjugation and alkene stability. And before we go over those concepts, I'm going to go over the 3-point concepts. So the first one is that carbocations are the most stable when they are more substituted. For example, a methyl carbocation is less stable than a primary carbocation, which is less stable than a secondary carbocation, and which is less stable than tertiary carbocation. This is because alkyl groups or R groups are weakly electron donating groups due to the inductive effect, and the more electrons that the carbocation is able to receive, the more stable it is. This is because reducing or delocalizing charges will give the ion stability, and this can happen through resonance or the inductive effect. So in this case, we see that we are increasing stability going from methyl to tertiary carbocation. In this video, I'm just going to go over these cases, but there are other cases where we have allylic carbocations where they can do resonance, which is going to be more stable than the secondary or tertiary carbocation, depending on what kind of allylic carbocation it is. The reason why the R groups or alkyl groups stabilize the carbocation is because of the hyperconjugation effect. We know that the R group has sp3 hybridized orbital with carbon and hydrogen, which has electrons in the orbital, and those electrons are able to donate negative charges to the positive charge because those electrons are free moving around the hybrid orbital. Whereas we see in these hydrogens over here, these hydrogens do not have sp3 hybridized carbon to hydrogen orbital, which is why they cannot inductively donate electrons due to the hyperconjugation effect. So the more R groups you have, the more stable the carbocation is. So now let's go over the alkene stability. Alkene stability is similar to that in carbocations, in that they are more stable when they are more substituted. So in this case, we see that we have an alkene in the middle right here with one R group, which makes this mono-substituted. We see in the second case that we have a alkene here with two R groups, which makes this di-substituted, which is why we see that the di-substituted alkene is more stable than the mono-substituted alkene over here. So let's do more practice problems. We see our alkene over here with 2 R groups, which makes that a di-substituted alkene. We see our alkene here has 1 R group, which makes this a mono-substituted alkene. We see our alkene here in our third case has 3 R groups, which makes this a tri-substituted alkene. So the most stable alkene here is going to be this tri-substituted alkene, and then the second most stable is going to be this di-substituted alkene, and then the least stable would be this mono-substituted alkene. So let's say we have 2 alkenes that are both di-substituted. We see here these 2 alkenes are both di-substituted because they have 2 R groups. How do we tell which one is more stable? Would it be the cis alkene where the R groups are facing the same side, or would it be the trans alkene where the R groups are facing away from each other? So in this case, we have to look at a different factor, which is going to be steric hindrance, which basically means that the R groups are touching each other. That would be less stable. So in this case, we see in the cis alkene, we have the 2 R groups facing the same side, which has a high likelihood of touching each other, increasing the steric hindrance, which makes it less stable. Whereas in the trans alkene case, the 2 R groups are facing away from each other, making them avoid steric hindrance, and that would increase the stability. So that is why trans alkenes are more stable than cis alkenes, because they have less steric hindrance.